Okay, so let's get started today. If you did not get your exam, have still exams to get back. You can get them after class. And today, going to go over the midterm coding solutions, also the coding solution to the after class assignment from Thursday, so you can see how recursion works. And today we're going to be talking more about trees and more about recursion. And again, recursion is hard, so it just takes practice in seeing many examples and comparing the examples and seeing differences between them. And slowly you will start to get into kind of a groove with it and a feel for how you state a program recursively. So that's the agenda today, and we will start with the midterm exam, the coding questions. And I'm not going to spend a huge amount of time going over them. Just note a few of the common errors that were made. So the first one asked you to iterate through an STL list. And the STL list contained pointers to users, and what you were doing was simply returning the average of their weight. So if you visualize it, what the STL list looks something like, it's a doubly linked list with Sentinel nodes, and each value pointed to a user. So the value, whoops, I didn't want it going that way. So the value fields pointing to users, and each of them has a weight, which I'm just going to show as W. So what you needed to do was iterate through the list, accumulate the weights, divide by the number of users, which is the same as the size of the list, and that would be your average. So one thing that many of you are still forgetting to do is to pass your objects by reference. You also may not be reading as carefully as you should because 8 here was remember to pass all object parameters by reference. Okay, so this is important. When you don't pass your object references, your object parameters by reference, you really slow down the running time of your program. And I took off a point for failing to pass your objects by reference. Okay, then a few of you forgot to initialize the sum to 0. That can lead to problems because on the Hydra machines, the compiler does not initialize your integer variables to 0. And then you simply needed to iterate through the list, which most of you got. What some of you had trouble with was extracting the weight. So what you had to start with was getting the pointers. So when you say starlet with a list, that gives you the value. Starlit gives you the value of the node. Well, in this case, the value of the node, that is it. That's what a list stores. When you instantiate a list, you tell C++ the type of the value that list is storing, which in this case is pointers to a user. So in this case, when you say starlit, what you're getting back is a user star. So you now effectively had, you could even have said user star u equals lit, which is what some of you did. And then it seems if you did it that way, you'd know that you would say sum plus equals u with an arrow weight. But you can collapse all that into one line by first doing the parentheses. The parentheses right here tell the compiler that we want to do the dereferencing operation first. Otherwise, it's not necessarily clear whether it's going to do the arrow operator first, so if I just wrote lit wait, you run the risk that the compiler is going to interpret it this way, which would give you an error message. Okay? So by putting the parentheses around the star lit, I make it clear to the compiler that the first thing it should do is dereference the iterator and return the value. I think everything else should be pretty clear, although the other common thing was to use a counter variable to keep track of the number of users when the number of users can be obtained using the size function. And you might think, well, what's the bother, or why not just allow us to keep track of the count of users? Well, a handful of you messed it up when you kept track of the count of the users. The biggest problem being forgetting to initialize count to 0. So anytime you do unnecessary work, you risk introducing bugs into your program. Plus, it really was double performing a task, because every time the list has something added to it, it's also adding one to its counter variable. So by keeping a count variable on your own, it's duplicating functionality. So there's multiple reasons why, if possible, you should take advantage of pre-existing functions. And this was an example. The size function was an example of a pre-existing function. So any questions about the list code? Okay. So then the second problem, you were asked to score a contest. Users were presenting you with problems they solved, and only the first solver of a problem received credit for it. Subsequent solvers of the problem did not receive credit for it. So if you were doing this by hand, if you had no computer, you would probably keep two lists. One list would be a list of the problems already solved. And when the user presented or contestant presented a problem, you would check this list, and if it wasn't yet on the list, then you would add it to the list. So this would be your new one. And you would keep a separate list, which would probably be your tally sheet. And that would keep track of contestants and their scores. So when a new problem came in and that user would get credited for it, you would either add 1 to the user score, or if it was a new user, you would add the user to the tally sheet and give them a count of 1. So you would be keeping two lists. If you did this by hand, we can map these lists to a set and a map. The problem solved is best implemented as a set given the constraints I placed on the problem, which is I forced you to use sets and maps. Okay, so given that I forced you to use sets and maps, problem solved can be implemented as a set because I only need to keep track of one value, which is the key. I don't need a key value pair. I only need to keep track of the problem. And then the tally, I called it contestants, can be implemented as a map where the key is the contestant name. So that is contestant name. And int is the score. Okay? So when I did it, I read in the name and the problem. First thing I check to do is, if I'm doing it by hand, has the problem already been solved? And if the problem has not been solved, then the problem is not in the set, and I will get back a pointer or iterator to the Sentinel node. So if it's not in the set, it will be equal to problems.end. So in that case, I add the problem to the problem solve set. Then I try to find the contestant on the tally sheet. If the contestant is not on the, if the contestant is on the tally sheet, then I will not have a pointer to the Sentinel node and I can increment their count. Otherwise, I set the contestant's name to 1, I added them to the tally sheet, I treated the map as an associative map, and I added the contestant to the map. And some of you had issues with the iterator. So with a map, the iterator has 2 fields, first and second, and you use an arrow to get access to the fields. So it does mimic the iterator for a set and a list, where you also, it's much like a pointer, because to get the value with the set or list, you dereference them with the asterisk. So all iterators effectively come back as a pointer, but the map iterator has 2 fields, so you get at its 2 fields using the arrow. And first is the key, second is the value. Okay. Now, if the problem could not be found, I didn't do anything. Some of you were a bit aggressive and always added the contestant to the tally sheet, regardless of whether the problem the contestant was the first one to solve that problem. And I wasn't a big fan of your aggressively adding names to the tally sheet, because if it was a really large contest, many of your contestants might have a score of 0. And so you were unnecessarily adding contestants to the map. I didn't take off points, but I didn't like it. Okay, in fact, I may have taken off a point. I forget whether I did or didn't. But I didn't like it because if the contestant did not solve the problem first, and they're not yet in the map, you really should not be adding them to the map. Okay, so after I did this, after I had processed all of the contestants, then I had to find the winner. So to do that, I made a pass through the map, and I simply looked at each score and calculated the maximum in the normal way. Some of you set max to be the score of the first person in the contestants. That's fine. I knew that the no score could be less than 0, so I set it to 0. That's fine too. And then I made a second pass to print the winners, because there was no guarantee that there was only one winner. I said there could be ties. So I made a second pass through the map to see whether there were any, to print out all of the winners. And because the map is in alphabetical order, I knew that when I went through the map, I was printing the winners in alphabetical order. Now, some of you kept track of the winning score up here. So after the else statement, some of you would say something like, if this contestant score is greater than max score, then you reset max score. And that was fine. So keeping a running total of max score was fine. Okay, oftentimes you would do it anyhow because you would like to keep a leaderboard. So when you if you did that, then this first loop was unnecessary and only the second loop was necessary. So that was fine. I had no problem with your doing that. Okay, perhaps the way you did it was a little slower than the way I did it. The reason is if there was a lot of problems solved, you did this comparison every time, whereas I only had to do the comparison once for each contestant. On the other hand, I had to go through the map, and here you didn't have that overhead. So I was fine with that. I was a little less fine with some of you trying during this step to keep track of the winners using a set. And the reason I wasn't a huge fan of that was that you had to keep clearing the set and then adding winners to the set. So some of you, to be clear, some of you introduced a set here in this loop, and you kept track of the current winners or in a set. But the problem was every time you found a new max score, you had to clear the set. And if you insert into a set, it's a log n operation. The map was already sorted. Okay, it was already in alphabetical order, so it's kind of a waste to be resorting them when it's not necessary. Okay, now I didn't let you do this, but if you were going to do this in practice and keep track of the current winners in a set, keep track of the current winners, think about this for a moment, you already know the contestants are in sorted order. The map keeps them in sorted order. So if you were going to try to use this technique, what is a better data structure to use to keep track of the current winners in alphabetical order? Remember, I didn't let you use this data structure. I said you were limited to sets and maps. But what would be a better data structure? Pardon? A vector. Because you know they're in alphabetical order, so if you simply added each new winner to the end of the vector, that's an order 1 operation, not an order log n operation. Now, I know I didn't give you the option of using a vector, but I'm not a fan of doing it that way. It's a lot of overhead. Everything was in alphabetical order anyhow. Either make a second pass through the data or do what other students did, which is keep track of the maximum score up here. Okay? Another thing that I noticed is that some of you treat this operation like it was constant time, and it's not. It's log n. And so many of you were not hesitant to use this 2 or 3 times rather than saving the value. When you use it 2 or 3 times, you're being wasteful because it's a log n operation. And every time you perform it, you're doing a find operation. So if you, with a map, if you save the value if you're going to reuse it. It's not like an array where it's an order 1 operation. It's a costly operation in the scheme of things. So save the value if you're going to reuse it. Don't say things like if contestant, I'm going to abbreviate it, name equal something, and then later on say foo equal contestant name. That's really inefficient because now you've performed a order log n operation twice. So you need to be saving values in that case. Now, this isn't the most straightforward way to do it, but it is more efficient, and some of you figured it out. You can do the insert and the find simultaneously. So with the problem set, you can both try to insert and find at the same time. And the way you do that is you insert, and the insert returns, the insert always has to do a find anyhow, to find where it should go in the tree. Okay? The reason we're doing trees now is because sets and maps are implemented using trees. So before we can do the insert essentially does a find. And if the problem is already in the set, insert returns a pair indicating A, whether the insert succeeded, and B, it gives you a pointer to either the inserted node or the pre-existing node. So I could combine the find and insert. I simply check then the second field, which indicates whether the insert succeeded or not. If the insert succeeded, the problem wasn't already in the set, and I needed to increment the tally. And then if it needed to be incremented, I could pull the same stunt with the map. I could attempt to do an insert by making a pair, and if the insert, no matter what happened, whether the insert succeeded or failed, it's going to return an iterator that points to the node. And so then I simply retrieve the iterator. It's the first field that comes back. The result is a pair. The first field is an iterator to the node, and the second is whether the insert succeeded or failed. I have no interest in whether the insert succeeded or failed. Okay? No matter what, the contestant is there, and at this point, I can increment their count. So that was a way to combine the insert and the find operations, thus collapsing two order log n operations into a single order log n operation. This isn't even the way I did it the first time, but I saw a couple students do it this way, and I thought that's pretty cool because they were saving time. So I figured I'd show you the solution. By no means did I expect you to do it this way, and it's definitely not as easy to read as this solution was. Okay, so questions about that? Okay. So, moving back to recursion. The problem I gave you for the after class exercise was how to find the height of a tree. Okay? And I gave you the recursive definition, so it wasn't all I really wanted to see is could you implement the recursive definition. What many of you, though, are having problems with is not how to implement it, but how to phrase the problem as a recursive problem. So you're having trouble coming up with a recursive definition. So there are different, what I would call, categories of recursive problems. Okay? One of them is like the Sudoku and Shapeshifter problems. So those are game problems where what you're doing is searching and backtracking. Okay, both the Sudoku and the Shapeshifter are being done over a grid. And you're basically systematically searching through that grid. And if you get to the end of the grid and some condition is satisfied, then you say you succeeded. Okay, so in this case, coming up with the base case is the grid is completely filled in. Some way you test to see if the grid is completely filled in, and if it is, then you indicate that the problem has been solved. If it's not correctly filled in, you indicate false. It has not been correctly solved, and you backtrack. So here the base case is essentially the grid is completely done, and you check it for some condition, and it's yes or no. Okay? And the smaller problem is typically moving. In Sudoku, you move to the next empty cell. With Shapeshifter, you move to the next shape. So that's one kind of problem. It's kind of a searching and backtracking. Another type is kind of a generation or enumeration problem. So the enum problem that you were given on the Lab 9 is one example. Fibonacci numbers is another example. N factorial is another example. Okay, these are all kind of generating or enumerating a sequence of something or other. Okay, so in those cases, the base case is a very simple problem that you can solve. For example, with n factorial, the base cases are 0 factorial and 1 factorial, which are equal to 1. With the Fibonacci numbers, it's Fibonacci 0 equals Fibonacci 1 equals 1. With enumeration, we went through the fact that there were 3 different types of base cases. I'm not going to do it again. Go back and look at your notes from the previous lecture. We went over the different types of base cases for enumeration. One of them, I'll just go say one of them was if you had an empty string, which means of length 0, effectively of length 0, that was the empty string. Okay, but you could also say, for example, enum, if you had just a string of length 1, then that was a forced solve 2. If you had a string of length 1 with 0 ones, it had to be a 0. And if you had a string of length 1 with 1, 1, it was forced to be a 1. So in these cases where you have generation enumeration, you're generally given base cases for the smallest possible instance of the problem, and that's solvable. And then you have to come up with a recursive case for where it's a smaller problem, and then you combine the results. So for the Fibonacci numbers, actually for n factorial, the recursive case is n times n minus 1 factorial. So the recursive case is n minus 1 factorial, and the recombination is the multiplication by n. With the Fibonacci numbers, Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. So the smaller recursive cases are fib n minus 1 and fib n minus 2, and the recombination is the plus. Okay, for enum, you have a length and the number of ones. So I'm not going to completely give it away, but as a hint, you have 2 subcases, one with strings starting with 0, and one with strings starting with 1, and the combination is a union operation. So it's plus, so this is a concatenation and this is a concatenation. And what you want is all strings of length n minus 1 headed by a 0. And here you want all strings of length n minus 1 headed by a 1. So you have 2 subtasks here. One to generate all strings of length n minus 1 headed by a 0, and one to generate all strings of length n minus 1 headed by a 1. And the result is a union. You union the 2 sets. In effect, you get back 2 sets. Now, in the enumeration problem, you don't actually explicitly generate the sets. Instead, as you find each valid string, you print it. And the reason you don't actually explicitly generate the set is that there's an exponential number of strings when enum gets fairly big. Okay, so this is your second type of recursive example or problem that you've seen. And you're doing both types in Lab 9. The third type is on trees, which is what we're considering now. Okay, and the base case with trees tends to be you do something with a leaf, because a leaf is a single node. Or sometimes you do it with an empty tree. So the base cases with trees tend to be things on either the leaf or the empty tree. And then your recursive case tends to be something you do on the left subtree and the right subtree. So you'll typically do something on the left subtree and the right subtree, and then you combine those operations in some way at the root. That's the recursive case. Do something on the left tree, do something on the right tree, and then combine. Okay? Do something on left tree. Then on the right subtree. Then combine. So that's the third kind of recursion. So one thing that can help when you're considering a recursive problem is trying to slot it into one of these three categories. Those are the three categories you'll see in this course. And then that might help you in coming up with your base cases and your recursive definition. So with the tree problem, the tree height, you were working with this tree recursion. So let's take a look at it. So actually here I gave you the base cases. I said that the base case was an empty tree. So the height of an empty tree was -1, which meant that the height of a leaf was equal to 0. That's another way to state the base case, is that the height of a leaf was 0. And then the height of the root is the maximum of the height of the left subtree and the height of the right subtree plus 1. So remember I said with trees, recursion is typically do something with the left subtree, so find the height of the left subtree. Do something with the right subtree, find the height of the right subtree. And then combine the results. So take the maximum of the two and add 1. Okay, so I gave you the definition of a node, left, right, and key. The key was completely irrelevant. All we cared about was left and right. And the bottom of the tree, a leaf node, had no pointers to its left and right. So here was the complete thing. Here's the base case. If the node is null, so you're given initially you're given the root node. So if the node is null, you return -1. That's the base case. The tree is empty. Otherwise, straight from the recursive definition, we calculate the left height and the right height by calling height recursively on the left and right subtrees. So you'll note node left is a pointer to the left subtree, node right a pointer actually to the root of the right subtree. Then I do my max check. So if left height is greater than right height, I return left height plus 1. Otherwise, I return right height plus 1. So that's just combining the max operation with the plus 1. But it's pretty much a straightforward implementation of my recursive specification. The actual hard part of this problem was specifying the problem recursively by specifying the base case and the recursive case. So questions about tree height? Okay. Now, does anyone who's looked at the notes remember what kind of traversal this is called? This is the kind of test question I would love to ask. Okay, so in order is one where you first visit so if you have here, in order first visits the left child, then it visits the parent, and then it visits the right child. So it's not quite doing it that way, because we're first visiting the left, what we actually have, what we first visit the left child, then we visit the right child, then we perform some operation to combine them. That makes it what? Post order. Very good. So this is a post order traversal. It's the most common type of traversal because you can't often solve the problem until you have looked at both the left subtree and the right subtree, and then you combine the results. So this is an example of a post-order traversal. And there are three common types of tree traversals. So now we're going to move back toward trees, okay? And we're going to, again, be focusing more on the recursive aspects, although I will also go over delete, because I know that delete is the toughest of the operations. I think insert and find you should have pretty much gotten from doing the readings for last Thursday and today. Although if you have questions on them, I will be more than happy to answer them. So going back to here, Dr. Planck, one of his first things he showed you was an expression tree where he was breaking algebraic expressions and representing them as trees. So this division was the root of the tree, and then this expression right here became the left subtree. This expression became the right subtree. And again, in order to evaluate this, if you actually have values for A and B, you need to do a post-order traversal, because before you can perform this division operation, you need to know what are the values for this expression, and you need to know the value for that expression. If you don't know the values for those two expressions, you can't very well perform the division. So in order to solve it, you need a post-order traversal, because you first need to evaluate the left subtree, then you evaluate the right subtree, and then you combine the results. So that's, again, you would evaluate this using a post-order traversal. So when do we use the other traversals? There were two other traversals, pre-order and in order. So we'll go over in order first because it's a little more natural. In order, you first visit the left subtree, then you visit and do something with the parent node, and then you visit the right subtree. Okay, there's not a lot of examples of using in order, but there's a very important one. If I ask you to print the values of a binary search tree in order, so print the values of a binary search tree, BST is how I'll abbreviate it, in order, then you use in-order traversal. Can someone tell me why you would use in-order traversal to print the values of a binary search tree in sorted order?
The leftmost branch would be the smallest value.
Would be the smallest, so the leftmost branch is the smallest.
And then as it traverses, the rightmost would be the least.
That's right. And then the root is in the middle. So basically, what you know from a binary search tree is that everything in the left subtree is less than the parent, and everything in the right subtree is greater than the parent. So if you print everything in the left subtree first, then you print the parent, and then you print the right subtree, as long as you correctly printed the left subtree and the right subtree, everything will be in sorted order. And we simply apply the same recursive printing to the left and right subtrees. And as long as we do that, we'll be just fine. And the base case would be a leaf. When we get to a leaf, we just print the leaf, because one node is obviously already in sorted order. So that is an example of in order. Okay, for pre-order, it's actually fairly unusual. Does anyone ever use a pre-order calculator? No, it used to be that HP made a pre-order calculator for some reason. Don't know why. If you use, how many people, I doubt it, have ever programmed in the language Lisp? I didn't think so. You'll get that opportunity if you take 365 from me. Well, it turns out you can express operations in prefix. So saying plus 3 and 6 says add 3 and 6. Then divide this by 2 says this is really 3 plus 6 divided by 2, but this is called prefix order because the operator comes first. So if we want it to print out this tree in prefix order, so for example, it could be evaluated in Lisp because in Lisp everything is done in pre-order. Pre-order says that you visit the parent first, then the left subtree, and then the right subtree, which is exactly what pre-order is. So if you want to print a BST, or I'm going to say print an expression tree in prefix notation, use pre-order traversal. So that would print out the operator, that would print out the divide operator first. And then if you go and look back up at this expression tree, it would print out the plus operator next. If I was doing it in pre-order. Then it would go next to here. Then it would go next to the star. Then it would go next to the 5, and then to the A. And then it would come back all the way up to here and come down the other side. So that would be printing out the expression tree in pre-order. So those are the 3 common types of traversals of a binary search tree. Okay. Now, pre-order is going to come up a lot too in the way that you implement find, insert, and delete. Now, the most common way to do find and insert is simply with iteration because it's the most efficient. So if you look at Dr. Planck's code for finding things, remember in a binary search tree, the way that you, let's go to the top, find, insert, and delete. The way that you find something is you compare your key. Let's say I'm looking for Luigi. You compare your key with the root. Since Luigi is greater than Binky, you go to the right subtree. Then since Luigi is greater than Fred, you go to the right subtree. And Luigi is less than Luther, so you go to the left subtree. So if you look at the find code, way down here, first of all, he's making left and right be his pointers to his left and right nodes. He's making string be his key, and we'll get to a void star in a moment. So just hold off on the void star. But if you look at his find code, he's keeping a sentinel node again. So he is assuming that instead of having his leaves point to null, he's going to make his leaves point to a sentinel node. So if it's a leaf node, he has them point to a sentinel node. And in fact, it's the same sentinel node. It's not like there are 5 sentinel nodes here. In fact, he has them point to the same sentinel node. So these are all the same. And again, by doing this, he's going to remove a lot of special cases that the book has. So his code's going to be a little simpler than the book because he's going to use a sentinel node. So his sentinel node is actually the root of the tree. So if we look, actually go back over here, his sentinel node is also the root of the tree, and the right child is the actual root. So that's the way his tree looks. So when you go to find a string, he first needs to get a pointer n to the actual root of the tree, and he does that by saying n equals sentinel right. Then he goes into an infinite loop because he knows he's either eventually going to get to a sentinel node or he's going to find the key. So there's 2 so-called base cases. The first one is if he gets to the sentinel node, he knows the key was not in the tree. So he returns null. If you get to a sentinel node, you effectively searched through everything that you could and you didn't find it. The second case is if he finds the key at the node, he returns its value. The third case is if the string is less than the key at the node, in which case he goes to the left subtree and he repeats the search on the left subtree. Otherwise, he knows it must be in the right subtree, so he searches the right subtree. Now, this is not a recursive function, but you could very easily implement this as a recursive function. In fact, I will probably make it the after-class activity for today, is to implement this as a recursive function. Okay, so can someone tell me what are the base cases? Right here. The base cases are looking at you. They're not hiding here.
You said them, right?
Yep, I said them. I even said them. So what are they? This is not a trick question. Yep. So the 2 base cases are, there are 2 base cases. Base case 1 is you don't find it and you're at a sentinel node. Base case 2 is you find it. So those are the 2 base cases. And then these are your two recursive cases, setting it to left and right, but you have to do it recursively, so through a recursive call to find. So I will have you do that as an after-class activity. I will force you to do that as a recursive function. Okay, and we call this is a pre-ordered traversal. Can someone tell me why the way, in effect, I'm traversing this tree is pre-order? What is the first thing that I'm doing?
You're
Dave?
performing an action.
You're performing an action. My first thing is that I'm checking the base cases. I'm performing an action at the root. So the first thing I'm doing is at the root, is I'm checking base cases. And then I'm effectively doing something on either the left or right child if the base cases aren't in play. So if the base cases aren't satisfied, I'm either going to go to the left or the right subtree, depending on the comparison of my search value with the key, or my search key with the key at the node. So this is, in effect, a pre-ordered traversal. I do something first at the root, and then if I'm not at a leaf, I go either left or right. And insert and delete are very much like this. Okay, if I'm at a leaf, I do something. Otherwise, I go either left or right. So in effect, insert, find, delete are all pre-order operations. Now, there is something you have not seen before, and that is a void pointer. So I'm going to come all the way to the top and find his first. So you haven't seen this before, void. When you have used maps and sets, you have said something like set string, and the value is the type that you put between the inequality signs. Okay, we don't want to have to burden you with how you define a template. It's a pretty complicated thing. We go through it in 365, which is Survey of Programming Languages. So to simplify things, Dr. Planck still wants to be able to store an assortment of values, and C, which is what C++ is based on, provides a generic pointer. So void star is a generic pointer. Okay, another way to think of it is as an untyped pointer. It means that anything that is a legitimate pointer can be stored in a void star. So any legitimate pointer can be stored in a void star. Okay, it's a bit like float and int, right? Because a void star is a more general form of a pointer. A float is a more general form of a number. And just like you can store an int into a float, you can store a pointer into a void star because it's a more general form of it. Okay, mathematicians in here probably recognize, what is it, a partial, Missy, you're a math major.
Oh, what?
Sorry. Isn't this something like a partial order? So void star is generic. Legitimate pointer can be a void star. So isn't there kind of a lattice. I'm not, my math is failing me.
What kind of math is that? I don't know if
It's discrete math.
I
Okay, you may not have had it.
Yeah.
That may be the issue. Okay. So when you get to discrete math, you'll probably get to something called lattices. And this is saying that this type is a more general type than this type. So you can store this type into this type, or you can store this type into this type. But you can't go the other way. If in C you try to say int x equals 6.3, you'll get a warning, because that is going to lose information, right? Same thing, you can say, if you have int star x and void star p, you can say p equals x, because you can assign a legitimate pointer to a void star. However, you can't go the opposite way. If you try to say x equal p, you will get an error message from the compiler. Why do you think if you try to just assign p to x, you might get an error message? Okay, I'll help you out. Why might the compiler not like x equal p? Well, I'll go.
For data types, like here you have a char and then it's assigning to an int pointer type.
Right, so what happened was I can assign any legitimate pointer to a void star. So I went ahead and I assigned a char star to that p. Well, now when I assign p to x, that's not an int star pointer that's sitting in p. P is pointing to a char star. So the reason I can't pull off this operation is there's no guarantees that P is pointing to an int star. P, as a void star, can point to any pointer it pleases. So C++ will give you an error message. So you might say, well, void stars look pretty useless to me, Brad, because it's like a black hole. Once I assign the int star to P, I can't get it out of there. You just told me when I try to go back and assign it to an int star, C and C++ will give me an error message, just like a black hole. I can put it into the black hole, but then I can't grab it out of the black hole. But I can get it out of the black hole using something called casting. So you've seen casting before. So if I say x equals int star p, what I'm doing is I'm telling the compiler, don't worry, take it on my word, I promise, I promise it's a int star. Now if it's not an int star, you will crash and burn. So this is something, again, that hackers can exploit if you're not careful. But it's a boon because it does give you a lot of control. So what you're doing with the casting operation is saying it's all good, don't worry, I'm guaranteeing to you there's an int star there. And if there's not, you're in trouble because C++ will take you at your word. It will assume it's all okay when you do that cast operation. Okay, so that's how you would extract the value from a void star. This is called a downcast. Technically, the word is a downcast because you are downcasting it to a more specific type. You're going from a general type to a more specific type. So a downcast goes from a more general type to a more specific type. Okay, you were taught that you could do that with instant floats too. If you put a cast there, then the C++ compiler is fine with it. It will say, okay, I realize that you want to lose precision, and it will happily do what to that 6.3? Truncate it. It will not round it, it will truncate it. Okay, so that's what Dr. Planck is doing with his void stars. Are there questions about what a void star is? Just a generic pointer. You can assign any legitimate pointer to a void star, then you can, quote, unpack that pointer out of the void star with a downcast. Okay, as I said, I think find it, or insert is pretty easy, even with the parent pointers. Delete is the only one that I think is a little bit problematic. So the last thing I'm going to talk about, actually, let me talk about one other thing, and then I'll talk about delete. Okay, what we're trying to do with these trees is we would like them to be pretty much balanced. Okay, this one, despite the fact that it has no left child, is actually relatively balanced otherwise. We will find out on Thursday that there are ways to ensure balance. For example, if there's a really bad insertion order like A, B, C, D, E, F, we can get a very unbalanced tree. Okay, that's when we present it in sorted order. But if we present keys randomly to a binary search tree, in general, the heights of the two trees are going to, subtrees are going to be roughly equal. So in general, if keys are inserted randomly, most binary search trees are balanced, which means that for any node in the tree, not just the root, but that, which means that for any node in the tree, the heights of its two subtrees are roughly equal. And the roughly equal is, as we'll find out on Thursday, a critical element in how you determine balance. So you can define that in different ways. By this definition, where we say that for any node in the tree, the heights of its two subtrees are roughly equal, is this tree balanced, or is it imbalanced? Imbalanced. Why? There's no left subtree for Binky. So if we look, Kalista, Ernie, Luigi, Waluigi, they're balanced. Any leaf is balanced. Daisy and Luther are balanced. Fred is balanced. But Binky is not, because its left subtree essentially has 0 height, and its right subtree has a height of 2. So it's unbalanced. So that would not be considered a balanced binary search tree. But if it's balanced, then, so if a BST is balanced, then as the book said, its height is log n. And specifically with those little elbows at the bottom, which means the floor function. So if there's n nodes, its height is log n, which means if we are doing a find, an insert, or a delete, and we only look at one node at each level, we only look at log n nodes. So that makes the operations log n. Okay, and we omit the 2. Notice there's no 2 here. Okay, no 2. The reason is in computer science, we don't use base 10 logs. In computer science, we use base 2 logs. So unless you see a number after the log, it is log 2. And it's kind of, you can kind of see it if you have one node and it's balanced. There's 1. If it's balanced and it's 2 levels, you add 2 more nodes. If you add a 3rd level, you're always doubling the number of nodes at each level if it's balanced. So at every level, if it's balanced, you're doubling the number of nodes. So if you remember that the way you get log n is you have something. So effectively, each level doubles the number of nodes in the tree. Okay, if you remember the old thing about the lily pond. Okay, if it takes 30 days, if lilies on day 1 you have 1 lily, every day the number of lilies double. And after 30 days, the lily pond is half full. How many days does it take for the lily pond to become full? 31. Because it doubles every day, on the 31st day, it will be full. Kind of like a tree. Each level adds actually, if the previous tree had n nodes, the next level actually adds n plus 1 nodes because each level, in effect, doubles the size of the tree if it's balanced. Okay, I'll let you ponder that. Also, I will tell you, if you are looking at code and trying to figure out how it works, you really should draw pictures. The programs are now getting sufficiently complicated. I don't go over the code a whole lot in class anymore because, quite frankly, having me recite code to you, you're not going to learn it that way. The cognitive research or the research on cognitive psychology shows you're not going to learn it by passively listening to me. We're at the point where the code is getting complicated enough, you're going to have to trace this code yourself and draw diagrams if you really want to understand it. Okay, kind of like I did with the insert function or the find function. But I will go over the basics of the delete because it is a little more complicated than any of the other operations for a binary tree. So let's go back. So with a binary tree, it's very easy to delete a leaf. That's not a big deal. So if we delete Calista or Luigi or Waluigi, no problem. Okay, so that's the first case. The node has no children. It's a leaf node. The second case is also pretty easy, where we're deleting a node that has just one child. So here, if we delete Binky, right here, it has just one child. All we do is we promote the right or left child, whichever it is. So it's one child replaces it. So when we delete Binky, we just have the tree you see here. If instead we were to delete Daisy, which has one child, Calista, which is its one child, replaces Daisy. Right there. You can see that Calista became the left child of Fred. So again, it's very easy if you have only one child, then that child replaces you. The only difficult case is where you have two children. Okay? So let's say that we wanted to delete Fred. Problem is Fred has 2 children. So what we do, and it's arbitrary, we can do one of 2 things. We can find the largest value in the left subtree, or we can find the smallest value in the right subtree. So basically, we're going to find the value closest to Fred. In this class, we will use 1. We will find the largest value in the left subtree. The largest value, I'm going to go over a couple minutes, the largest value in the left subtree is guaranteed to not have a right child. Why? You're nodding. Why is it guaranteed not to have a right child if it is the largest value in the left subtree? Very good. So if it had a right child, that right child would be bigger than it. So it couldn't be the largest. That's a very simple proof by contradiction. So the largest value in the left subtree cannot have a right child. So that means we can delete it using case 1 or 2, which means case 1 or 2 applies. Either it's a leaf or it only has a left child. So what we're going to do is, after finding the largest value in the left subtree, we are going to delete that node, delete the node with this largest value, and 3, we will store this largest value in the, I'm going to put it in parentheses, deleted node, because it's not really deleted. So the node, this deleted node in the original, I'll call it the original node. So we're not actually going to delete that original node. So here, Fred's node will not get deleted. The node that will actually get deleted is Fiona, which is the largest value in Fred's left subtree. So Ernie is going to become Daisy's right child when we delete Fiona, and Fiona replaces Fred. So in fact, Fred does not get deleted, or his node does not get deleted. His value gets replaced by the largest value in his left subtree, and it is Fiona's node that actually takes 1 for the team. So down here, Ernie, right here, Ernie has become Daisy's right child, and Fiona has replaced Fred. I encourage you to look at the code for delete. It is not trivial, and you really need to draw some pictures to understand what is going on. It is using a recursive call to recursively delete Fiona from the tree. Okay, this is important, and I will post it on Code Assessor because I forgot it until just now. I will not be here on Thursday, so no class on Thursday, but watch the video lecture. There is a quiz, and complete the quiz and the participation. So I am at a conference, but watch the video, complete the quiz, do the participation activities, but I will not be here Thursday. I'll be back Tuesday. Yes, Chris? I will not. Sorry. I have office hours today. I will be on a plane tomorrow. Pardon? There will be a code assessor problem today. I will post it. It will be a fine problem for binary search trees.
So wait, when does that do the code assessor problem?
The code assessor problem will be due, I'll make it Saturday. So you have some time for it.